Hi folks, we're going to talk a little bit more about two-dimensional collisions and we're going to do another example problem. Momentum is conserved in multiple dimensions. Two-dimensional collisions, meaning things that have both X and Y motion, those are really useful in accident reconstruction, or if you are a big pool player or billiards player. You are pretty good at this if you play a lot of billiards. Because of the fact that momentum is a vector, you have to keep that dimension in your mind. Here's just a couple pictures that I thought are just brilliant pictures of pool shots. Because they have the time-lapse photography, you can kind of see the smudge of the balls. So if here's the cue ball coming in, this is giving lots and lots of momentum to this whole rack of balls. Afterwards, there's a little momentum this way and that way. And all of the sum of the momentum has to be equivalent to the original momentum of that pool ball. So you get little smudges left and right because the left and right momentum has to cancel each other out. But the big forward velocity is going to be in the vectors of these two balls and taking that momentum in those directions. And again, the left and the right have to cancel because the pool ball just came in straight like that. Here's another really great shot. The momentum came in from the cue ball right there. Again, there is majority of the momentum is going to be forward. A little bit of left and right momentum has to cancel each other out. Here's your cute little 8 ball in the middle, almost not moving at all. And then you've got a little backwards momentum due to all the close to elastic collisions in there. These I thought were just kind of wacky. I don't know why. There's something about exploding fruits and vegetables that are interesting. But these are really slow-mo pictures of an exploding pineapple, exploding watermelon. And the math would be hard, really hard, if you took every one of these little chunks and the angles and the velocities. But your brain can see all these vectors in all these different dimensions would add up back to 0. All right, we are going to now go and do a example problem. So here goes. I am going to have a problem about some speeders. So we have Zelda is traveling eastbound with a car of a mass of 2250 kilograms. Sinbad, in his hot little red sports car, collides with her in the intersection. And it doesn't say what direction he's going. He was going south. My bad, but he was southbound. The red sports car has a mass of 1300 kilograms and was going at 33 meters per second. When the police accident investigator examines the wreckage, she notes that the wreckage makes an angle of 57 degrees east of south. If the speed limit in the area is 45, who should get a ticket? Zelda, Sinbad, or both of them? Well, first off, let's do a little conversion. If I've got 45 miles per hour, if I get rid of hours, go to seconds, 3,600 hours in a second. Oh, I said that wrong. 3,600 seconds in an hour. Get rid of miles, go to meters, and this is going to be 1609 meters in a mile. I end up with just around 20.1 meters per second. So if Sinbad was going 33 meters per second and it's supposed to be 40 is the speed limit, oh yeah, he's going to get a ticket. But what about Zelda? Now, we don't know her original velocity, so let's draw a picture of this situation. Again, we're going to have an intersection. So let me draw a little intersection here. I have Zelda in her car. This is the big Z for Zelda. And I have Sinbad in his little red sports car going this direction, southbound, and Zelda happens to be eastbound. And they're going to collide right about here, and their wreckage is going to go that away. Now, the accident investigator found that the wreckage actually made an angle of 57 degrees east of south. So what angle is that? If this is straight south, this is 57 degrees here. And I have talked to police officers who actually do this, and they measure these angles and measure these skid marks in order to testify in court. And this is part of a momentum triangle, where this is going to be the momentum of this car, And this vector is going to be the momentum of Zelda. So I'm going to put Zelda's momentum right here. We want to know if she deserves a ticket as well. The car going south has a 33 meters per second speed, and it is 1,300 kilograms. So 1,300 kilograms times 33 meters per second is the speed. So for Sinbad, the total momentum on this vector is 42,900 kilogram meters per second. If I want to know the momentum of Zelda's car, all I've got to do is solve for this side. So here's my angle. This is my adjacent. I'm looking for this side, which is the opposite. The tangent of theta is opposite divided by adjacent. So the opposite side is going to be the tangent of theta times that adjacent. So this will be the tangent of 57 degrees. The adjacent is the 42,900 kilogram meters per second. So the momentum of Zelda's car is going to be 54,909 kilogram meters per second. Cool, that's her momentum. So how are we going to find her velocity? Well, you and I both know momentum is mass times velocity. So her velocity prior to this impact is going to be her momentum prior to impact divided by the mass, 54,909 kilogram meters per second, divided by the mass of her car, which was 2,250 kilograms. And so how fast was she going? Zelda was going at a speed of 24.4 meters per second. Speed limit in the area is just about 20 meters per second. Does she deserve a ticket as well? Yep, poor Zelda's going to get her ticket as well. All right, folks, that'll do. See you later. Bye-bye.